Let's play a game. I'm going to compete against you. We start with a pile of n stones. We take turns tossing out certain numbers of stones. If it's your turn and there are no stones left, you lose. On each of our turns, the number of stones we toss out must always be a square number. That is, it must be one of 1, 4, 9, 16, etc. We want to find out who wins if both of us play the optimal strategy. How can we find this out? We don't even know what the optimal strategy is. Well, for any turn-based game like this, there's a simple solution we can always use: a brute force-based approach. It's not very fast on its own, but it gives us a good starting point. Turn-based games in particular tend to give a nice structure to this approach. On your turn, try a move and then recurse for the next turn. If the recursion tells us that the player who played the next turn loses, then we won. And then proceed to do this for every possible move. If any of them let us win, then we can win by doing that move. In most games, including this one, such a brute force solution would run in exponential time. However, in many games, this brute force-based solution is easy to memorize. Whenever we recurse, the only parameter we pass is the number of stones. So, let's memorize the result for the number of stones. This gives us a dynamic program of size O of n. However, it still takes more time than this to run, since we have a large number of moves. In order to find the exact runtime, we need to know exactly how many moves we can make on each turn. Well, the moves involve taking a square number of stones less than or equal to n. How many square numbers are there less than or equal to n? Let's rearrange the equation. So, how many numbers are there less than or equal to square root n? There are, of course, at least O of square root n numbers, and hence O of square root n moves. So overall, this gives us a runtime of O of n times square root n. One of the most beautiful things about this approach is that we never required any difficult insight into the game itself. We merely had to simulate different moves and collect the results. As a last step, let's take a look at the iterative implementation for this problem, i.e. the bottom-up dynamic program. We can store our win results in a vector-based memo with indices up to n, just as before. Then, as our name suggests, we iterate through the different game sizes in bottom-up order. Note that the game of size 0 is already set to be false by default, which is a loss, which is correct. Next, iterate through all the possible moves, again, just like before, but now, instead of recursing, just look at our memo. If the move causes the other player to lose, take it. Finally, return whether or not we can win in our input game of n stones. That's some short code. If you found this video helpful, please share it around. These animated tutorials are very fun to make, but also a lot of work.